so making this work might be a bit of a challenge without some creative housing plans. Regardless, this does seem like a good solution to the energy crisis. The jewels are there, so if we can already cover our population's needs by fully accessing only a small fraction of the sun's total output, the part hitting the Earth, we probably don't need to harness any more of it just yet. However, looking to the future, that won't always be the case. Reaching 40 trillion people is actually not that far off, at least on the scale of human history. Our population is currently growing at a rate of 0.88% a year. At times, this number has been as high as 2%. For simplicity, let's just take a nice round 1% figure and calculate using that. If we increase for the population size by 1% every year, the cumulative growth of the population would hit 8.8 billion in a decade, 22 billion in a century, and 40 trillion in only 800 to 900 years. So what might be the solution when that happens? Why doing, as Dyson's hypothesized alien races do, and increasing the amount of solar energy that we capture, probably by building solar panels or mirrors and sending them into orbit around the sun. As the course I was learning from highlighted, with more solar collection tools comes more benefits. A Dyson sphere, or a Dyson swarm, as this segmented configuration is technically known as, offers power that's many orders of magnitude higher than what we can do with just a planet's worth of surface area. Harnessing it would elevate us to a higher level of civilization, one that went from controlling its planet to harnessing its entire solar system, perhaps giving us the springboard that could truly kickstart our expansion across the stars. On the Kardashev scale, a method of measuring a civilization's advancement by evaluating how much energy they could potentially use. This would tip us from a Type 1 civilization into a Type 2. In case you're wondering, we're currently only about a Type 07, as we've not quite managed to make use of all the energy on the planet. While a Type 2 would have access to all the energy in the solar system, to get to a Type 3, we'd have to harness the entire galaxy. So that's a long way off. Still, the energy levels a Dyson sphere could produce are already so extravagant, it seems silly to our current understanding to even contemplate them. If we completed a Dyson sphere or a Dyson swarm, we would go from 4.7 septillion joules to 10 decillion joules, increasing our energy levels by 20 trillion times. That should be enough to keep the lights on for the foreseeable future. Technologically speaking, we are pretty much at the point where we could make a solar panel that could capture sunlight from the sun and send it towards Earth. Or even easier, we could simply create space mirrors to reflect the light towards where we needed it, say, an orbiting space foundry outside of Earth's atmosphere with the same end result. This might be the simpler idea, as then you don't have to worry about how to transfer all the generated electricity from the solar panel back to Earth. You can just send the sunlight directly to wherever it's needed. Although you would be sacrificing some habitability on the Dyson sphere itself, placing mirrors into stable orbits is not impossible for us, and having them be able to maneuver slightly to reorient through the year doesn't sound too implausible. So then it's just a question of how much materials would this require? Unsurprisingly, depending on what distance you created your shell, a Dyson sphere would need a lot of material. For instance, the course I was learning from identified that building a Dyson sphere that coincided with the Earth's orbit would need about 6% of the entire volume of the planet, even if the panels were less than a millimeter thick. This is hardly ideal, even if we could selectively drill out the materials that were needed. But if we instead built a sphere at a much more compact distance from the Sun, say at the distance of Mercury's orbit, then the material requirements become much more feasible. Mercury itself contains all the raw material that might be needed for such a structure. And as far as we know, there is no one living on Mercury who would complain if we were to fill it with holes. But then, the last issue to consider, other than the moral question of whether it's okay to tear apart an entire planet purely for our own benefit, is that it's obviously an energy-intensive process. Materials have to be mined, processed, then made into their components. The solar panels or mirrors would need to be built, and even once that's done, they need to be lifted out of Mercury's gravity well. and that's a particularly energy-intensive process. If we utilized all the sun's energy that was hitting the planet Earth and spent it all on doing nothing but lifting mirrors. For our Dyson sphere out of Mercury's orbit, we can calculate how long it would take us to lift enough mirrors to complete the entire shell. We know the formula for overcoming the gravitational binding energy of Mercury, which for Mercury gives us roughly 2 times 10 to the power, 30 joules. We already know how much energy we at maximum could get from sunlight here on Earth, 4.7 times 10 to the 24 joules. So then it's just a simple matter of dividing the first by the second, and voila. This process would only take a measly 425,000 years, during which time there would be no energy left to support Earth's population or give light to our plants, because we're using it all to build the Dyson sphere. Maybe this isn't such a viable idea after all. But wait, there's one last point to factor into this. That's the fact that once our mirrors came online, they could start providing energy of their own to help pay the energy costs. This would then become an exponential process with no additional input required from Earth. Perhaps, except for a little oversight, one mirror would provide energy to make a second. Then both would double to make 4. Every instance, you would be doubling your number of mirrors. And once you get exponential growth involved, depending on how much energy you put into the system at the start, the entire thing could be completed much sooner. According to some calculations, Mercury would be completely disassembled in as little as 31 years. In other words, if we started building one right now, you might live to see its completion. Ethical considerations aside, such numbers really bring into focus the viability of this project. Something that takes half a lifetime to complete is certainly ambitious, and the initial cost might indeed be great. There would be some practical considerations to think about in terms of the best way to set up mining operations on Mercury. But these are questions we're already putting our minds to anyway. Scientists are currently working out how to set up bases on the Moon with similar intentions. We're not far away from doing the same on other planets once we have the techniques down. In other words, there really aren't very many barriers left towards attaining the immense energy of the Sun. A Dyson sphere might well be another example of something that sounded like science fiction to us, but will turn out to be something our children or grandchildren will one day come to take for granted. Thanks for watching. If you like this video, please subscribe our channel Fact 13.